All right, it looks like we're recording. The slides are shared. I think we're ready to go. We're going to be covering a lot of topics today. We've covered kind of the essentials of the C Standard Library in little bits throughout the semester, especially really early in the semester. But there's a lot of things that we haven't managed to cover yet, and we're going to try to fit in as many of those as we can today. If I can talk fast enough and not dwell on details too much, I think we might be able to get through all of these topics, and then we'll just have a few left over for next time. Any questions before we get started? I don't know if I said, welcome to day 18 of CN Software Tools. So we'll, like I said, mostly be talking about the standard library today. What is the standard library in C? It's kind of like the API that you get with the Java language. It's all of the IO things that you need. It's a lot of support for string manipulation, a bunch of standard things you need to write a program that does something in C. It's not nearly as big as what Java has with its built-in API, but it accomplishes some of the same things. Like I said, it provides IO, it provides support for floating point computation, lots of little parts of the language. If you wanted to look and see what was in the standard library, I think the right place to look for how it's organized is the collection of headers. Many of these, or at least some of these, you've already seen. The header files advertise little parts of the standard library, and the three that I've listed. So if you want to understand what's in there, that's one way to kind of get a survey. I've listed here some of the earliest ones. Well, some that we've already seen. We saw limits, which among other things tells us the bounds on the built-in types for the language. We saw standard bool and assert already. We've made in most programs, we've made use of standard io.h and standard lib.h and string.h for string manipulation, especially since about 10 days into the semester. These are ones that we haven't used as much, or ones that we'll see today. There are header files for manipulating characters rather than whole strings, for getting error message output, for working with math operations. All of these I've colored in blue because these are ones that I'll expect you to know. So you should know what math.h is and what kinds of things are in it. We'll talk about this one a little bit later. ctype.h, you should know what that is and what's in it. But I said there are 24 of these, which means, and we've only looked at maybe 10 or 12 so far. So there must be a bunch of them that we're not going to cover in too much detail, and that's what I've listed here. There's these, looks like 8 or so, and then 5 more on this page. And this is just to show you what else is there that we're not going to have time to cover in this class. Functions for handling wide characters. If, say, the ASCII character set isn't enough to let you write the kind of programs you need to, there are parts of the language that'll let you do that. Parts of the language for doing different kinds of math, like math with complex numbers. Parts of the language for using different types of character encoding besides ASCII characters. These are all there, and it's probably worth it to know that there are parts of the standard library to support things even if we don't use them. But we won't cover this too much in this class. We will go back and cover a few more things that we skipped over earlier. And one quick thing we can cover is things you can do with strings. We covered a few things out of the standard library for string support. Things like measuring the length of strings or copying or comparing strings. We've already seen functions like A to I. There are a few special purpose or special variants of these functions that are worth knowing. You already know about string copy. And I know when we talked about it, I give you a warning that it doesn't have any way of checking the bounds on the destination string. So if you try to copy a giant string into a short little array, it's going to buffer overflow that array, which could crash your program or overwrite something important. And this is a really easy mistake to make with string copy, because like I said, it doesn't have any good way of knowing how big the destination array is. There is a good friend of string copy called string copy. You can see it's got an N in there. I colored it in red up at the top of the slide. This you can think of as a bounded string copy. That N sets a limit on how many characters it will write to the destination buffer. Otherwise, it works just like string copy. It takes, in fact, here's the prototype for it. It takes the destination buffer you want to write to, the string you want to copy into that, but then you have to help it out by giving it a bound N. And that's a bound on how many characters to write to the destination. So like I'm doing down here at the bottom, I'm copying from a source string to a destination, but it won't write more than 10 characters to the destination. In fact, what it does is it copies, and this is maybe an easy way to remember the behavior of this. It zero pads up to this length. So if you give it a source string and a destination string, it'll copy everything from the source to the destination. If it gets to the end of the source before it has used up N characters, before, in this case, before it's written out 10, it'll just keep writing out zeros until it gets all the way up to 10. And that's what I'm showing at the bottom of this slide. If you copy a short string into a bigger buffer and you tell it, well, I want you to write out, or I've got room for 10 characters. It'll copy the whole short string and it'll pad or it'll fill the rest of the characters, however many you tell it. Up to that bound, it'll fill them with zeros. And this is kind of handy. It guarantees that the rest of the buffer is initialized with something, even though usually that doesn't matter. If you're thinking of this as a string, normally you would stop at the first null terminator and you'd never even look at the rest of these characters. And this behavior is a little inconvenient when the destination buffer isn't big enough to hold the source string. This is why I made a big deal out of the behavior you get. It copies as many characters as it can, and then it pads the rest of the space with nulls. What if there's no rest of the space? What if you tell it, well, here's how big my destination is, and then you give it a source string that's even bigger? Well, it'll fill everything in the destination, but if there's no leftovers, and it won't buffer overflow, if you tell it you've got room for 10 characters, it'll only write out 10. But if there's no leftover space, it won't write down any zeros at the end, which means it won't even null terminate your string. And I would say that's bad. That's what this function does. That's what, when they designed the language, that's what they decided it should do. It's just that seems like a bad choice to me because it could easily give you a string that's not null terminated. Now, they haven't fixed this in the language because there's kind of an easy way to fix it yourself. You just need to be aware that if you have a destination buffer that's, say, 10 characters long, and you copy over a string that's longer than that, it'll copy over the 10 characters, but it won't put a null at the end. If you want to make sure you get a null terminated string in the output or in the destination, you've got to plan for that yourself. And this is what I said a moment ago. It's not too hard to do that. It's just something you have to worry about as the programmer if you want to use this function. So the normal way to use this is to tell it one character shorter. So if you've got a destination buffer that's 10 characters long, you can tell it to copy over at most 9 characters, and then put a null at the end yourself. That's really what this code up at the top is doing. If I've got a buffer, and I've been calling it a 10-character buffer because that's easier to say, but we could ask the compiler how big that buffer is, and as long as we're in the scope of a declaration, it can tell how big that array is. We can back up from 1 character from that and tell string copy to copy over that many characters. And then, like I said, we could go in and put a null terminator in that last character space ourselves. If the source string was short enough that string copy put some nulls at the end, putting this extra null at the end doesn't help, but it doesn't hurt. And in the special case, when the source string is too long, it'll fill up every character except that last one because we told it to stop 1 byte early. And then in this next line, I just always put a null there at the end of ourselves. So this is kind of the standard way to take the behavior that you get from string copy, the bounded one, and get it to always give you a null terminated string. Any questions about this before we move on? I said there were a few functions that we skipped over, and this one we didn't cover at all, string cat. String copy copies a source to a destination. String cat is for concatenation. It adds the source to the end of the destination. So if you, like my picture shows, if you had a destination string that had the word apple in it, and you called string cat and put the string pie at the end, it would add on whatever's in the source to the end of the destination, starting from wherever the null was. That used to be the end of the source string. So it'll start filling in characters there until it's copied everything from the source. And then it'll put a null terminator at the end. Just like string copy, this one doesn't really know how long your destination buffer is. And since you're adding two strings together, it's maybe even easier to buffer overflow the destination, which is why for this one, maybe it's even more important that there's a bounded version of this function, string cat, with the extra n in the middle. So backing up, this one's called strcat. And this one is strncat, and the n is for that bound n. It works just like string cat, takes a destination string and a source you want to add to the end of it, and how many characters, well, a bound on the number of characters. I hesitated there because it's a little tricky to say what the bound means. For this function, that bound n is a limit on the number of characters it will add to the end of the string. I tried to show this in my picture at the bottom. So if you try to build a string apple, and let's say you concatenate on a bigger string like orchard to the end, but you give it a bound n. That bound is taken as the number of characters, a limit on the number of characters to add after what was in the first string. So it means to prevent buffer overflow, you got to think a little bit about how much room you have left in the string. And that's kind of what I'm showing in my last example. I guess if you had a buffer with 10 characters and you knew you already had 5 characters in it, then you've got room for 4 more characters along with the null terminator. And I haven't said this yet, but let me go ahead and say it. Unlike string cat, this will always put a null terminator at the end. So it'll copy the source onto the end of the destination, copying no more than n characters, the number you told it to copy, and then it'll always stick a null terminator after that. So when you're figuring out the bound to use for how many characters you can afford to copy without having a buffer overflow, you got to plan for that. So it seems like you would want to say, well, how big is my buffer in total? 10 characters in this example, minus how big is the string that's already there, minus 1 more for the null terminator that needs to go at the end. And that's how much room I have to add on more characters. And that's what I did right here. If size of works, if you're in the scope of the declaration of this array, you can say, use size of to say how big is the destination array, minus how big the string, how many characters long the string is that's already in that array, minus 1 more for the null. And that should give you the right bound for how much stuff you can afford to copy. Questions? All right, moving on. One more string function, at least one more general purpose one. We've already seen string compare. There's also a bounded version of string compare. It's got an extra n in the middle. Remember, the regular string compare is strcmp. strncmp will compare characters between the 2 strings you give it, just like string compare. It'll look at characters until it finds a difference or until it reaches the end of both characters. But you can get this one to stop early. If you give it a bound n, then even if it doesn't see any differences between these strings, it'll stop after it's looked at n characters. If it sees a difference within the first n characters, it'll report that just like string compare does. But if they match all the way up to the first n characters, this one will stop at n and it'll just return 0. It'll return as if the strings are the same. So this is maybe an easy way to compare just parts of a string. Maybe the first part of a string, or since you can easily look anywhere you want in a string using pointer arithmetic, this would let you compare any little part of a string with another string, even if there wasn't a null terminator at the end of the part you wanted to look at. Questions about this? All right. A couple of we don't need to talk about these because we sort of already talked about them. In preparation for project number 4, I recorded a little video talking about scanf, and I posted that already. If you haven't watched it already, I would go back and watch that. It's several lectures ago, but it's labeled as a short lecture about scanf. I won't repeat that content right now, but make sure you go back and watch that, even if you didn't watch it as you were getting ready to do project 4. scanf, as you know from that video, it's a handy way of parsing what's in a string using exactly the same format string syntax that scanf and fscanf use. So it's nice to be able to use that to parse input that's already in memory. And this is kind of why functions like a to I are not as important, because this can do any conversion that a to I or a to f or a to long can do. These are in that short video, so examples how to use scanf, this trick for seeing how many characters you've parsed so far. I don't remember if that video covers this function, so I'll try to cover it quickly, with some risk that, that this is going to be duplicated. For the people who are there in the lecture, do you remember, did I cover this already? I'm thinking I didn't, because you probably didn't really need it for project 4.
Yeah, this isn't in the video.
Okay, good. Thanks for speaking up. Yes, so I'll try and do a good job of covering it now. You know what this function does. If scanf is for reading from a string instead of from a file or standard input, then this one must be for writing to a string. And that's exactly what it does. This lets you, whereas printf sends output straight to the terminal, this lets you send output into memory. It lets you write it into a string, and then you could potentially do other things with it besides printing it out or before you print it out. It's just like fprintf, except for the destination, instead of taking a file, it takes a string given as a char pointer. So it's counting on you already having a string that you've already allocated, and it's just going to write characters into that string. So kind of like the other functions, it would be easy to buffer overflow with this. If you wrote out a bunch of output and the string wasn't big enough, this could easily write past the end of your buffer, which is why there's also a bounded version of this. snprintf takes an extra argument near the start. So what string do you want me to write to? How big is that array? How many elements long is that char array? And then format string and any other arguments you need. And the behavior of this function is it won't write past the size that you tell it. In fact, it will plan ahead and actually stop one character early so that it has room for the null terminator. I think of the behaviors we've seen a bunch of functions that accept a bound like this. This is the one that makes the most sense to me. This is the one that I think is easiest to work with, because you just have to tell it how big your buffer is, and it will write out characters staying within your buffer length, and it'll even plan to leave one extra character, and then it'll always put a null terminator there. So the example at the bottom shows this off. I've got a buffer that's 10 characters long, but that means it's got room for a 9-character string plus the null terminator at the end. When I call snprintf, I just have to tell it 10, the length of my buffer. And even though I told it to print a string that's much bigger, it'll stop after 9 characters. It'll put a null terminator at the end, and then leave my string so it didn't buffer overflow and so that it's always null terminated. This is awfully handy, and obviously it goes with the previous function, scanf, for reading input from a string. This just lets you write output to a string. We've said, and I've kind of disappointingly said, there are different behaviors. We've seen 4 different functions that all take a bound, but they all use that bound a little bit differently. And there's no good way to, there's no good rule. I think they all kind of have a different rule for that, and I'm sorry about that. That's kind of what we're stuck with in the language. You remember our first one, string copy, pads up to the length n with zeros, but it might not actually null terminate if the destination buffer isn't big enough. String compare just compares the first n characters, stopping either at a null terminator or when it hits length n. String cat, the n is a bound on the number of characters that it'll copy to the end, and then it'll put a null terminator after that. Whereas the one we just saw, string or SN printf, n is a bound on the number of bytes it will write to the destination buffer. It'll always stop one character early and then put a null terminator after that. So it'll stay within your bound, but it will make sure it gives you a null terminated string. Questions before I move on? We've already seen these 2 functions. We saw them when we were learning about resizable arrays, memcopy and memmove. These are declared in string.h, even though that maybe seems like a weird place for them to be declared. I'm reminding you of these because there are a couple of other functions that we haven't talked about yet, like memset. It's also declared in string.h, but instead of copying memory, it's good for filling memory with a particular value. It takes 3 parameters, a pointer to the memory you want to fill, the value you want to put in every byte of that. So even though it's writing out bytes, this is still declared as type int, but it's going to put a copy of that value in each byte of the buffer. And then how many values you want to put there. So this could be handy for zero filling an array before you start using it, or putting a bunch of, like down here, I'm pretending I've got a n by n map, maybe a 2D array, and I'm going to fill it with copies of the dot character before I start using it. So a handy way to zero fill, or really to fill memory with any byte value you want before you start using it. We've looked at a number of string functions, and there are a bunch more that we're not really going to get a chance to look at, but this is kind of a reminder of what we've covered and some other things that you might find handy, even though we won't be able to cover them. We covered these functions for copying strings and measuring the length of a string. I'll remind you, all of these depend on the string being null terminated. So string length works because it goes and looks for the null terminator that marks the end of a string. String copy knows how many bytes to copy because it copies until it hits the null terminator, and then it copies a null terminator. String comparison functions. String comparison is kind of made to work with a standard ASCII character set. But in some environments, in some places, you may have rules for comparing characters that are different from the order of ASCII characters. There's a locale dependent version of string compare. I put it in gray here because I don't really expect you to know that. But if you were writing code with more concern for internationalization, or if you were writing it in a place where they didn't use the same ordering of characters that we use in English, then functions like this could be awfully handy. We've seen functions for concatenating strings. There are a bunch of functions for tokenizing strings, or for looking for things in strings. And that's what I've listed here. I know on project 4, several people found this strtok function, and they used that to break the the movie list, at least every movie up into its fields. I don't know if that really made it easier, but that's the kind of thing this function is made to do. I mention these just to say if you had to write, if you had to do some real programming in C as a working software developer, it'd be worth it to know about some of these extra functions. All the stuff in string.h is for working with whole strings. It's kind of like what's in the string class in Java. C also has functions for working with just one character at a time. And that's kind of like what you see in the character class in Java. The header file for these is C type. So you can think of that C as character type .h. And there are a bunch of functions for testing different kinds of characters. I've listed a bunch, well, I've listed a few of them here. I'll just expect you to know the first four of these. Those are the ones that I use most often anyway. There's a is alpha that you give it a character code and it returns true or false if that's a letter. There's an is space. It returns true or false if the character you give it is a white space character. So I think there are 6 white space characters, spaces, horizontal and vertical tabs, new lines, things like this. This function knows which ones are considered white space. So you can ask it rather than having to code that yourself. There's a function for asking if something is a digit. So that'd be a decimal digit from 0 to 9. Asking if a character is printable as opposed to a control character, and then a bunch of others that I listed, a few of which I listed in gray. You don't need to know these, but it's worth it to know that there's a pretty big set of tests you can do on characters. You can see some here you might want to know, like, is it an uppercase character or not? And I'm just expecting you to know a few of these. C-type has functions for testing what kind of character you have, and it has some functions to do basic conversions like to upper and to lower. To uppercase is a character. So you give it a character, it gives you back the uppercase version of that character. If it's not even a letter, it just gives you back the input unchanged. So if you wanted to uppercase a string, this would be an easy way of doing it without, you just go through all the characters, call to upper on them, and then take whatever it returned and replace the character with that. Same idea for to lower, you give it a character and it gives you back the lowercase version of that. I just covered several functions. I'd like to give an example of them. So I wrote this little fragment of code. It's not super useful, but it takes input and tries to break it up into words. So it replaces arbitrary input with space separated words using some of the stuff that we just talked about. Sorry, and it prints out all the words in lowercase as it does that. So it goes through and it reads from the terminal. So it keeps getting characters over and over again until it sees an EOF. And then for the character that it just got, if that's for the character that it just got, it wants to skip white space because we're just going to print words with spaces in between them. In fact, I said that wrong. It's going to skip anything that's not a letter. So it's going to try to find the start of the first word. So as long as it sees something that isn't a letter, I'm using this is alpha that we just talked about, I just keep reading characters. You know, I worry that, well, what if I hit the end of file while I'm trying to do that? So I put in a condition to get me out of this loop if I hit the end of file before I start seeing the start of a word. So this skips everything up to the next letter. And then I'm going to print out the sequence of letters I see as if it's a word, but I need to separate them. And I apologize, I also said this wrong a moment ago. I think I said the words are going to be space separated, but looking at this, it looks like it's going to print each word on a line by itself. So if I saw a letter and it wasn't the first word I've seen, I print out a line break before I start going through the next word and printing out its characters. I skipped over this a moment ago, but I use this flag to tell whether or not I've already printed a word. This is essentially, it's a fence post loop so that I print new lines between the words instead of always printing a new line at the start or always printing a new line at the end. All right, and then once I've printed a new line before the next word, I go through all the characters in the next word, and as long as it's a letter, I print it out, but I uppercase it before I print it out. And then I go ahead and try and get the next letter. So this should print, it should take any sequence of characters as input. It should find the words and print them out one per line using a few of the functions that we just talked about. We've mostly been talking about string and character functions. There are several things you can do with standard IO that we haven't used up to this point. And I've listed some of the things that we'll take a quick look at. Ways of detecting when you've hit end of file, ways of noticing and recovering from file errors. So let's talk about those. First, here's a function that I encourage you to never use. It's some people have found this function, and there's nothing really wrong with it. It's a function for detecting if you have hit end of file on any stream. It's called FEOF. You call it and you pass it as a parameter, a file pointer. So that could be a file that you opened. It could be one of the standard streams like standard input. It returns true if you've already hit the end of file on that stream. Otherwise, it returns false. What don't I like about this function? Well, the reason we haven't covered it so far, and the reason I said what I said a moment ago, I encouraged you not to use this function, is I've seen a lot of bad code written using this function. And here's an example of it. So here's how you might normally try to use this function. Let's say I want to read a bunch of integers until I hit the end of file. So I've got a loop that calls fscanf to read an integer and store it in a value, and then maybe I'll process that value. And then I'll just keep running through this loop as long as I haven't hit the end of the file. So as long as FEOF returns true, as long as FEOF returns false, I'll stay in this loop. When it does return true, I know I've hit end of file, so I'll bail out of the loop. There are two problems with this code. And the first one is what I'm trying to illustrate at the bottom of this slide. This is very sensitive to exactly what happens at the end of file. If your input looks like this, so you got a number and then maybe some white space and then another number, and then the file ends right after that second number, then this code will behave the way you want. After it's read the 102, you're right at the end of file. So FEOF will return true. You've reached the end of file, and it'll bail out after processing these two numbers. But this next input, where you just have a new line or maybe some white space or anything like that, after the second number, this loop is going to keep on going in that case. You're going to read the 25. You're not at the end of file, so you'll read the next number. It'll skip the white space. You'll get the 102, but then you're still not at the end of file. There's this new line character after the 102. So you'll stay in this loop. You'll call fscanf and you'll say read the next number, but if the file ends right after this new line, it won't get a number. But if you don't check that, and you can see in this code, I'm not even checking the return value from fscanf, then fscanf is going to return 0. It's not going to change your value. But if you don't notice that, it'll look like you got another copy of this 102. It'll just leave that value unchanged because FEOF doesn't tell you whether there's no more values to read. It just tells you whether you've hit the EOF or not. In fact, to work, you have to have already tried to read at the end of file. All it does is remember if you've reached the end of file. And these two examples are showing that off. Let's pretend you had some input that was just maybe 3 characters, 1, 2, 3, and then here, pretend the file ended right after that 3. Well, if you read each of those characters one at a time, and then you ask, am I at the end of file? It's going to say no. because you haven't actually read past the end of file yet, or you haven't tried to yet. So as far as it knows, you haven't reached the end of file. You'd have to try to read another character for it to know that. But if you read those same 3 characters like this, if you say, read me an integer and store it here, well, it'll read the same 1, 2, 3 and store it in this val field. But if you ask FEOF here, it's going to say true, you have hit the end of file. The reason for that is, well, while it was reading this integer, it had to read these 3 characters, and then it had to try to read another character just to know that there were no more digits. It'll remember that, and FEOF will say, oh, I know that you're at the end of file here. Whereas over here, even though you've also read 3 characters, you didn't try to read past that. So FEOF will return false over here and true over here. This is one reason I didn't feel like we needed FEOF. I've seen, like I said, a lot of people write bad code using that. And I think we've had, or at least I think you tend to have a lot more success by detecting EOF, end of file, by trying to read something and then seeing if that's succeeded or not, rather than trying to use a function like this and look ahead to see if you're at the end of file or not. When you do hit the end of file, that's something we just saw, that's something that the stream remembers. In fact, there are a lot of error conditions that it can remember. Like if the disk gets full and you can't write anything else out to a file, or if you've tried to create files and you already have the maximum number of files you can create, or you've reached a maximum file size. Whenever that happens, the stream remembers that it's hit an error condition. And in general, you can ask it, have you encountered an error condition, by calling this function. So this is kind of like FEOF. It just reports whether or not that stream, something has gone wrong in that stream. So you can check on it later. You just give a pointer to the file as the stream and it returns true if it has reached an error condition, like the various conditions I'm talking about up here. And that error condition will stay set until you close the file, or you use this function. If the error condition, if some error condition happens and you want to try again, say you tried to write to a file and your disk was full, and maybe you went and deleted some stuff to free up some disk space, and now you ought to be able to write to that file, calling this function, clear error, will clear the error condition, and it will let you try to use that stream again. The error could happen again, but this would at least let you get a fresh try at whatever caused the error. So clear error, you give it a pointer to a file and it'll clear the error condition, and then you can use that stream for other operations if you want. Questions? I'm trying to move fast. We got a lot to cover today, but most of it's simple stuff. You've already seen this idea that streams do some buffering. Especially output streams, if you write a bunch of characters to them, they might not actually write them to the file right away. Normally, anything that you've written might be buffered until you close the file. But this function can ask to flush the buffer even without closing the file. Fflush, you can give it a pointer to any stream you want, or any file pointer you want, and it'll flush out the contents of the buffer, writing them to the file. This could be handy if you had a program that needed to be able to recover from errors. You might want to flush output frequently to make sure that you had as much as you could written out to disk. This could also be handy for debugging messages. I've seen people make this mistake, or at least this kind of mistake. If you print something out to the terminal, and you don't put a new line at the end, that'll usually stay buffered in memory until your program terminates. So if you print this message and then you wait for a while, and this sleep call will make your program wait for 5 seconds. During that 5 seconds, you won't see this first part of your output message because you didn't put a new line at the end. It stays buffered in memory. It'll all show up when you print the rest of this line, because this new line at the end will flush the output. Well, new lines will automatically flush output to the terminal, but this function will let you flush output to the terminal whenever you want. If you take the same code and sneak in an F flush right here before the sleep, even though you didn't finish writing out a line of output here, this will still get flushed out to the terminal and you'll be able to see it even before this, the rest of this line gets printed. And then when the rest of this line gets printed, it'll just show up after on the same line as what you printed up here. It'll just, this will show up right away rather than having to wait for the end of line. There's a type of IO. Questions before I try to move on? There's a type of IO that we haven't really done yet. All of our standard input streams and all the files that we've opened so far have been operating in text mode. That is, the C standard library assumes that they're made up of characters. It might even do some conversion of characters for us. You see this kind of thing with the treatment of new lines. Maybe if you're working on a Windows machine, you've wondered why you never actually see the 2-character line termination sequence if you're reading input on Windows. And that's because if it thinks you're reading from a text stream, it does some conversion for you. When you print out a \n, if you're on a Windows machine, it'll print out a 2-character sequence, even though you only tried to print a \n. This shows that text streams get special treatment. There's some conversion that's happening, and when you read a sequence of bytes in a text stream, you might not get exactly the sequence that's there in the input. Files can also be opened in binary mode, and when they're in binary mode, every byte you read or write from the file should be exactly what's stored in that file. On our next project, we're going to be working with some files in binary mode, so we need to make sure that when we read or write a particular sequence of bytes, we get exactly what we think we should. Sorry, it depends on how you say that. For reading, if you open a file and you read in 10 bytes, you want to know that you're getting exactly the 10 bytes that are in that file. By default, a new stream opens up in text mode, so it does some conversion for you. If you want to see exactly what's in that file, you have to open it in binary mode, and that's part of the mode string. You remember fopen? We've been using it for weeks now. It expects a path name per file you want to open and a mode, and we've always been using R for reading and W for writing. But you can invent a bunch of other modes, and that's what I've listed here in this table. If you say R+, you're opening a file for reading and writing. So you could read or write from that same stream. If you open a file with A as the mode, you're opening it for appending. It'll open it so you can write to it, but you'll start at the end of what's already there. It won't truncate the file and let you start from the beginning. And you can combine various characters to get other modes, like the last two in this table. If you put a B in the mode, like RB or WB, that's how you ask for a stream in binary mode. If you open a stream in binary mode, like I said, when you read a byte, you should get exactly the next byte of the input. If you write a byte, exactly whatever byte you write out should go to the output stream. And we already know a little bit about how to read and write individual bytes. fgetC and fputC would let us read and write 1 byte at a time. But these next two standard library functions are even more convenient for reading and writing a lot of binary data all at once. Here's fwrite, and the next one will be fread. And these are you can think of them as handy ways of reading and writing arrays of things. Not by converting them to text, but by taking what's actually in that array and writing it out to a file, exactly what's in memory, or the other way around, taking exactly what's in a file and putting it in an array. I've got a picture that shows this, how you might use this. So let's say this blue thing over here in memory is an array of ints. So pretend all the boxes are bytes. On the common platform, each int is 4 bytes. So this could be an array with one int here, the next int here, the next int in these next 4 bytes, and then one more int. This function, one of these functions that we're looking at, fwrite, it's made for taking a copy of what's in that array and writing out the sequence of bytes to a file. And then later, if you wanted to access that same array from a file, you could use fread to copy what was in the file straight into an array in memory. Let me rewind and talk about these two functions. So fwrite would be for taking the contents of an array and writing it into a file. It takes 4 parameters. You can use it to write an array of anything you want. You just pass a pointer to the start of that array as the first parameter. Last parameter is the stream you want to write to. So what file do you want that to go to? And the next two, kind of like with qsort, they describe the geometry of the array. The second parameter is how big is each element of the array. And the third parameter is how many elements are there. So in this picture, a couple of slides ahead, if I had an array of ints, every element is 4 bytes. So that'd be the size of each element. And at least in this picture, it looks like I've also got 4 elements of the array. So this I could write out with a call to fwrite. Every element is 4 bytes in size, and I want to write out 4 elements. Fread is for going the other way. Its parameters are almost the same, except you give it a pointer to the start of the array that you want it to put stuff in. So you better have enough room for whatever you're asking it to read. How big is each element of your array? How many elements do you want me to try to read? And where do you want to read them from? And this one returns how many elements it successfully read. So if you said, I want you to read 100 integers worth of an array, and there's not that much stuff left in the file, this will at least tell you how many elements it successfully read. So as an example, if you said read 100 integers, and there were only 200 bytes left in the file, now 200 bytes is only enough for 50 integers if they're 4 bytes apiece. So if you only had 200 bytes left, then to read in the file, it can only, on the common platform, it can only read 50 integers. That's what it would return. How many elements did it successfully read? So this would give you a way of doing I/O that wasn't text-based. And if you didn't need to look at it, if a human didn't need to look at your file contents, then this could be a lot more efficient. You wouldn't have to convert it to text every time you write out output. You wouldn't have to parse it from text every time you read it in. I've got an example program that shows this off, a couple of examples actually. Questions before we look at them? All right, this example does file copy using fread and fwrite. Lets us copy files in big chunks rather than just one character at a time. I open a file for reading and a file for writing, so a source and a destination file, but I'm going to access them just as a bunch of bytes, so I ask for them to be opened in binary mode. And then instead of copying from source to destination 1 byte at a time, I do it a whole block at a time. I make room for 1 kilobyte, 1024 bytes. And then over and over, I call fread. And I say, read a bunch of bytes. So each of them is 1 byte in size, but I got room for 1024 of those. Read as much as you can into this buffer. And as long as I'm reading something, as long as I'm getting a non-zero return, I turn around and write that many bytes to the output file. And I just do this over and over until there's nothing more to read. And then when I'm done, I close both of these files. So this uses those two calls to quickly copy a file from source to destination. This next example does what we talked about before. It takes an array out of memory and writes it to a file. And then the code at the bottom reads that same array from a file. Let me talk through this real fast. So I open a file, I call it list.bin. The .bin, I think of it as a file in binary mode. I'm just going to write raw binary data to it. And I open it for writing in binary mode. I make an array with 4 integers. I made a small integer and then a bigger one and then a bigger one and then an even bigger one. And I write out that whole array at once by using fwrite. I want you to take that array, so I give a pointer to the start of it. I want you to write it to the file I just opened. And I want to write out 4 things, each of which is an int in size. Code down here tries to read that same stuff back in. So this would be how you might do binary IO if you wanted to save something in a file, but it wasn't important to save it in a human readable form. You could just write out the contents of memory to the file. So here I open a file for reading in binary mode. I make room for 4 integers and I call fread to read 4 elements, each integer sized, into that array I just made. And if you run this piece of code, followed by this piece of code, or more typically, if these were in 2 different programs, you should get exactly the contents of this array when you read it in from the file. This also gives us a way to look at how stuff is stored in memory by looking at the contents of a file. And if you run these programs, or you run the first one, and then you look at the file it writes out. And since it's binary data, hexdump would be a good way of looking at that. Hexdump-c, we've talked about this a couple of times. It'll write out, or it'll tell you the contents of every individual byte in that file. So the first 4 bytes are 03000000. The next 4 bytes are D8010000. And then we wrote out 4 integers, so there ought to be 8 more bytes after this. But looking at what's in this file, we can tell something about how integers are stored in memory. Because if you look back at our source code, I just made up some integers, a small one, and then the next one I made a slightly bigger one, so 472. 472, if we convert that to hexadecimal, and if it's an integer, it's going to be a 32-bit hexadecimal value. So that's going to be 8 digits of hexadecimal. 472 is 000001D8 in hexadecimal. And if you look at this second byte, now these first 4 bytes would be the first int of the array, since ints are 4 bytes apiece. So these next 4 bytes would be the second integer in the array. We see a weird thing here. This D8 didn't go over on the right, like how we wrote it down here. The D8 was the first byte that got written out. So this is a 4-byte int, so this D8 would be in one of its bytes. This 01 would be in another byte, but the D8, even though we write it down on the right when we write down a number, that's the contents of the first byte in memory. The 01 came after it, and then these, and this example doesn't show it, but then this byte was stored in memory next, and then the high order byte got stored last. And at least on most computer systems today, this is how stuff's stored in memory. The low order bits of a number are stored first, or I guess a better way to say that is if you've got an integer and it takes 4 bytes to store that integer, the least significant bits, the byte holding the least significant bits gets written out first. And then the byte holding the next 8 bits, the next 8 bits counting from the least significant byte, and then the next 8 bits, and then the next 8 bits. We've got a name for this order, and it's called LSB first, And that's kind of what we were talking about, the least significant byte, the one that holds the lowest order bits, the one that holds, the one that in this example, that holds bits 0 through 7, the low order bits. That one gets written out first, and then the next one, then the next one. Sorry, I lost my train of explanation there. This is called LSB first, sometimes called little endian. You're starting with the little, the least important part of the number, the least significant bytes. Not all systems do it that way. We wouldn't have to. Some systems store bytes of a number the other way around. So given this same number, they would have put this 00 first in memory. And then this 00 and then the 01 would have gone here, and then the D8 would have been the last byte. And those we would call MSB first machines or big endian machines, because in memory, they start by storing the most significant byte, not the least significant one. But this shows us that our common platform machines, in fact, most machines you would use today are going to be LSB first machines. But not all systems are like that. And if you're writing data out to a file or you're sending it over the network, and you might be communicating with a system that has a different byte order, this is the kind of thing that you have to worry about. If you write out a file using binary mode like we're showing here, and you write it on a machine that's LSB first, and then you try to read that on a machine that's MSB first, the numbers won't look like what you wrote out because the byte order will be backward. You can fix this, but it's usually the job of the programmer to think about this kind of thing. If there's a difference in the order that bytes might be stored in memory, and we read in, say, an integer, and we know that the bytes are stored in the reverse order from the machine we're using, we just have to go rearrange those bytes, and it could be done with code as simple as what I wrote here. We could write a swap bytes function. You give it a pointer to an int, and it can go in and get each of the bytes of that int and just rearrange the values in memory. In fact, it's easy to do by taking the start of that int, pretending it's a pointer to a byte, going and getting the first byte and the last byte in that 4-byte chunk of memory and swapping those, and then getting the 2 middle bytes and swapping those. So this would let us change the byte order in memory. It's pretty easy to write a function like this, but we don't really have to write it ourselves. There are standard functions for doing this kind of conversion, because whenever you're working with binary data, and you might have to worry about working between machines with different byte orders, you might have to worry about correcting the byte order. I'll say for network communication, the way this is normally handled is there's a standard byte order for writing out data on the network. And any system that writes binary data to the network is expected to put that data in network standard byte order whenever it gets written to the network. If we were writing data to a file, we might have to worry about the same kind of thing. So in the last few examples, I've tried to show you standard library functions for reading and writing binary data. And I've tried to introduce this idea about byte order, how you can tell what kind of byte order you have, and how you can correct byte order if you need to. Questions? All right, a few other functions for doing I/O, and especially for moving around a file non-sequentially. Normally, if you open a file, especially if you open one for reading, you start at the start of the file, and then as you read, you automatically move forward to the file. And then when you get to the end of the file, you've hit EOF, and you've already seen everything that's in the file. What if you want to go back and take another look at what was in that file? Well, you could close it and reopen it. Or you could use this function for files that you're accessing sequentially. Rewind will automatically take your current position in the file all the way back to the start of the file. So if you wanted to reparse what was in that file, this would be a way of going back to the start and looking again at the contents of the file, start to finish, or as much of it as you wanted to. This is really a special case of what you can do with the fseek function. Rewind always goes to the start, but fseek will let you go anywhere you want in the file. Fseek expects 3 parameters. Fseek, you give it a stream, so what file are you reading from or writing to? Where do you want to go? That's the offset parameter, and you can see this is type long, so it's a large integer type to let us support really large files if we needed to. Where do you want to go? And then there's a parameter that is traditionally called whence, and it really means with respect to what. It's a constant value that lets you say, well, when I tell you where I want to go, is that with respect to the start of the file, or where I am right now, or even the end of the file? There are 3 constant values you can provide. I've listed them here, but these examples down at the bottom probably make them easier to talk about. If you say seek cur, then offset is with respect to where you are right now. You could give a positive number to move ahead in the file or a negative number to back up. So the example I'm showing here with a -1 and seek cur would back up by 1 byte in the file. Seek end says when I tell you offset, it's with respect to the end of the file. So seek end with an offset of 0 would take you to the very end of the file. Seek set is with respect to the start of a file. So here offset would just be the byte number you want within the file. If you say seek set and then give it an offset of say 5, then the next read or write you did would be at byte number 5 in the file. This works great for files that are in binary mode because every time you read a byte from the file, you automatically get the next byte from the file. There's no translation that's done. These functions are not as useful for a text file because, like I said, if a file's in text mode, as you read or write, you may not be getting exactly what's in the file. Sorry, something made me jump to the end of my slides by accident. If you're in text mode, fseek is not as useful, but you can use it in combination with this function, ftell. Ftell will tell you your current offset in a file, even if some conversion has been done on individual bytes as you've read them. It'll tell you how many bytes you are into the file. So if you read a bunch of stuff and then call rewind, you'll automatically go back to the start. If you read a bunch of stuff and then call ftell, it'll return an offset that you can use later. So without necessarily having to return to the start, you could read a bunch of stuff, call ftell to find out where you are, read a bunch of stuff later, and then go back to where you were when you called ftell by just using this return value as an offset. So this function is made for, particularly for text files, for figuring out where you are in the file and then returning to that position later. We've seen a bunch of functions for doing file I/O. There are a bunch more that we're not going to talk about too much, but you might want to consider some things that you might want to do with a file that you don't know how to do in C yet. Like, what if you wanted to remove a file or rename a file or just make a temporary file? There are standard library functions for this. There's a remove. You can just give it a path name and it'll delete that file if it can. If you've got a file and you just want to change its name, rename takes an old path name and a new one. If you just want a temporary file, temp file will give you a pointer to a new stream that is used as a temporary file. You can use that stream to store whatever you want, and then the file will automatically go away when you close it. So it's a temporary file that automatically cleans up after itself. I'm showing you these just to show some examples. There's a bunch of other stuff that's out there, and it's worth it to know at least a little bit about what's in the standard library so you can go look for it if you need it later on. One thing that we haven't used very much yet, we used it maybe in one of our first, I think our first project used the random number generator. Standard library defines a couple of functions for pseudo-random number generation. Kind of like the random number generator in Java, rand returns a pseudo-random number, so it goes through a computational process that outputs random numbers, random looking numbers based on that process. And when you call plain old rand, you get the next random number in that pseudo-random process. It's a number between 0 and rand max inclusive, where rand max is a constant that's defined in that same header file, standard lib. Unlike Java, when you call rand in C or whenever you start up a program, it restarts that same pseudo-random process with the same constant value. So if you ran the same program over and over again, if it used rand, it would get the same sequence of pseudo-random numbers every time you ran it. If you want to control the start of that pseudo-random number sequence, there's a way to seed it. This function at the bottom, srand, lets you supply a seed so that you don't have to get the same pseudo-random sequence every time you run a program. You can use the seed to get a particular sequence you want to use. So this lets you control how that pseudo-random process starts. If you want a different, or at least what looks like a different pseudo-random sequence every time you run your program, it is common to use srand seeding it with the time function. There's a time function, I think it's also declared in standard lib.h. And if you call it like this, if you supply null as the parameter, you can also pass in a pointer as the parameter, but if you just pass in null, it returns as its return value the number of seconds that have passed since January 1st, 1970. So this is how Unix systems normally keep up with time, or how they manage time stamps. And calling this function tells you a time number, an integer that changes once every second, and that has been counting seconds since the start of the year 1970. If you take that number and give it to srand, then you're going to get a pseudo-random sequence that's seeded with something that depends on the time. So every time you run this program, as long as you don't run it too frequently, it should start with a new seed for the random number generator, and you should get what looks like a different pseudo-random sequence. So this is a way of getting random numbers that look more like, random, that aren't always the same every time you run your program. And this is the kind of thing that Java does automatically when you create a new random number generator. It seeds that random number generator, I think, with something that depends on the time of day, or depends on time. What could you do? What else could you do with this random number generator? What if you don't want an integer in the range of 0 to rand max? Well, that constant is provided so that you can scale the output of rand to give you any range you want. This fragment of code generates a random number between 0 and 1 inclusive. It calls rand, but then it takes the return value from that, divides it by rand max, and I forced this to be a floating point division. Otherwise, this would, most of the time, it would just divide and truncate to 0. But by promoting R to a double and then doing the division, I get a floating point random number from 0 all the way up to 1, up to and including 1, because remember, rand returns a value between 0 and rand max inclusive. So it could return rand max, in which case this R divided by rand max would be 1. If it happens to return 0, this would be 0, or it could give you any value in between, or it could give you a bunch of floating point values in between. So this trick would let you get random numbers between 0 and 1, or you could modify this trick to get random numbers in any range you want. If you had some minimum and maximum and or range, let's say you wanted to generate a random number between some min and max that you picked. Well, if you know how far it is from min up to max, you can generate a random number between 0 and 1. This is the same trick we just did. Scale that up to how far min is or max is from min, and then add that to min, and then that would give you a random number between min and max inclusive for any min and max values you want. So the point is, the integers that rand gives you can easily be scaled and shifted to give you random numbers in any range you want. Questions before I try to move on? Maybe we've got one more function we can try to talk about. And one more feature of the language that we really haven't seen up to this point. You know that normally when you call a function and something goes wrong, like you call fopen, you try to open a file, and let's say you can't open the file. You can print out an error message, but how do you know why you couldn't open the file? There could be a bunch of different reasons you weren't able to open a file, or in general, whenever there's an error, there might be a bunch of different explanations for what that error is. The way to see the explanation in C is with a global variable called errno. That's a little bit of a lie. Nowadays, it's not really a global variable, but we'll think of it like a global variable. If you include errno.h, then you get a declaration for a variable of the same name, errno. This is just a plain old integer variable, but whenever an error happens, this variable gets set with a numeric code that indicates what went wrong. So let's say you want to call a function and something might go wrong. Like you want to call a function to open a file, and you want to know if the file successfully opens or not. And if it doesn't, you want to know why. Well, you can set errno to 0 to clear it. And then you can call that function. And then if the function fails, you can check errno. And like I said, it gets set to a constant value that says why something went wrong. And there are a bunch of names for those constant values, like e-access indicates a particular type of error. Now, how do you know what those names are? How do you know the different values you might get for errno? That kind of thing is all in the documentation for C. If you want to read, if you're logged into a Linux machine or in general a Unix machine, and you want to read the documentation for a standard library function, you can normally type man, that's for reading the online manual pages, and then the name of that function, and then in the terminal you'll get a printout of the documentation. Whenever I'll need a quick reminder of a standard library function, I usually do this rather than going to try to look it up in a book or even Google for it. This is an easy way to get the documentation. And down at the end, it says all of the different things that might go wrong if this function fails and the errno values for when those go wrong. So for fopen, there are various things that might fail and errno values you might get, say if you can't open the file for one reason or another, like the example that I'm showing here. So you could use this, you could have a little piece of code backing up a slide that checked the value of errno and printed out a message based on what went wrong. And you could just have a different message for each of the different errno values. I'm almost out of time, but let me say, that's why it's handy to have this function. So I said you could write a bunch of code that knew a bunch of different errno values and printed out a meaningful message for each different value of errno. But you don't need to do that because someone already wrote a function like that. And that's what p-error does. we're out of time, so I'm going to save this for the start of our next lecture, but we'll pick it up here. And this is a handy function. You'll use this in your next project. It's for printing out error messages that say more about what actually went wrong. Thanks for your attention. We'll save this for next time. And we'll talk about it at the start of lecture on Wednesday. I'll go ahead and stop recording, but if you have questions, hang around and I'll try to answer them.